second workshop I'm taking part here, and also I would like to thank the staff of Newton Institute for the excellent circumstances for research and for presentations, and also for the excellent stay here in Cambridge. So my talk will be on numerical methods to compute the nonlinear filter in the filtering problem. So this is a joint work with Nick Krylov, and today I will consider only one method. This is the finite difference method, finite different approximations. In the next workshop, I hope I can consider other methods and the acceleration of other methods. So the system or the model, the plan is first just to introduce the model, which is the same we have already heard talks about it, but in RD, not on manifolds. And then second, the finite difference schemes, and finally the acceleration results for finite difference scheme. So the following model is considered. The XY signal and observation process satisfy these SDEs. H and sigma and rho are functions. They can depend also on T. They are functions of the observation and signal. And the observation process Y is given in that form. A very general model can be, in fact, written in this way. So this is quite a general model. As usual, W and V is a Wiener process, D plus D one-dimensional Wiener process. So I write the signal process already in a decomposed way, which is pleasant to formulate the results later. So as everyone knows, the basic question is how to compute the functions, or how to compute functions of the signal at a given time t from the past observation, so from the observation until time t. And in L2 sense, the best estimate is the conditional expectation, which if the density P, the conditional density exists, can be written as the integral of phi of x P Tx dx. So P is the conditional density when it exists. So basic theorem from the Pardue-Krylov-Rozovsky theory is that if the initial conditional density exists and it is regular, so it is in W12 space, and if the coefficients, if the functions involved in the system are regular enough, so let's say they have bounded derivatives in x up to order 3, then the conditional density exists and can be calculated from the ratio written there, where ut is the solution of the Zakai equation, so which I have written down here. So L star and M R star are second order and first order operators. YR is the R's coordinate of the observation process. U naught, the initial condition, is the initial conditional density. And the operators L star, M R star are the adjoint of the operators L and MR, and you can see these are, so L is the operator which corresponds to the signal process, so that is the let's say infinitesimal generator, which is random because Y, the observation, goes into it. So therefore you see the definition of the So we consider random operators here, and the first order operator is of this form. Also, the why I wrote this H here, I wanted to write capital. Yes, this small h is the drift. So the drift coefficient, and the capital H is the drift, but in the signal process. Right, so this is then the equation we want to solve, and there are plenty of methods developed, and many of the contributors are here. So the chaos decomposition method, and splitting up methods, and particle methods, and so on. And the basic method is the finite difference scheme. So from now on, we in fact forget the original problem, and we consider the Sakai equation, and we try to solve the Sakai equation by finite difference methods. So more precisely, we consider such a problem, a little bit more general. This L is nothing to do now with that L plus, or there is something to do, but not the same. Gee, maybe I will use the notation which I use later. So here, so we consider this linear stochastic partial differential equation with an initial condition. L is a second order operator, so in this form, so A alpha beta, and it depends on Tx and also on omega. These derivations, d alpha, d beta. Alpha is running from 0 until d. The equation is considered in Tx belonging to 0 capital T cross Rd, which is later or now denoted by Ht. And when alpha equals 0, then it is just the identity, the unit operator, just to have a short way of writing, to have also the first order operators, and for different alpha. So when alpha is sum from 1 to d, then this means the derivation in the direction of the x alpha coordinate. And f and g are random fields, so functions of t, x, and omega, and assumed predictable and Borel measurable with respect to x. Similarly, the coefficients are assumed to be real valued here, and predictable in t and omega, and measurable with respect to Borel measurable with respect to x. Well, I haven't specified MR. MR is then B alpha R D alpha, and like here, it depends on t and x and omega in a measurable way, and B alpha, this notation is used. This is a sequence of functions in R from 1 to infinity, such that the values are in little L2. And the WR is a sequence of independent Wiener processes to have a general case, so cylindrical in effect is involved. in a way involved. Right, so this is the equation we consider, and what do we assume? So here are the assumptions. Maybe it is good to remember a little bit that is assumption 2.1 here, and it consists of 3 parts. The first one is just a symmetry, non-important condition, and the measurability condition. So that's second is regularity of the coefficients, that they are differentiable and with bounded derivatives up to a fixed order, which is m, and m is a fixed integer which is greater than or equal to 1. So dlx and the a alpha beta is less than or equal than a fixed constant k, and similarly for b, alpha r. Oh, in fact, this is in the L2 norm. So here L is less than or equal to m, and here L less than or equal to m plus 1. And the third is the well-known, we don't have here, parabolicity, stochastic parabolicity condition. So just for remembering stochastic parabolicity condition. Right, and then the next assumption is that the data entering the free data and the initial data are regular. So this is assumption 2.2, and maybe the notation k script km squared, which is the expectation and the integral from 0 to t. Yes, maybe I should stress that the notation in index m means that in x the Sobolev norm, the Hilbert-Sobolev norm with differentiability index m is considered. Here there is a t and plus g n plus 1 and dt. Oops, the dt is there, all right. Plus the initial condition. Yes, m plus 1. And this must be finite.
Why you not should be m plus 1?
Where? For f?
You not. Why it should be in the norm m plus 1, not f?
That's. I think this is the right. So I formulate the result, and then hopefully it will be all right. This is, I think, that must be the right assumption. So the solutions are looked in that product space. So maybe we should remember that the W or boldface W with a T here and M and 2 means the functions which are L2 in omega and T and with values in the Sobolev space Wm2. And so we look for the solution in that case, and if the previous assumptions are satisfied, then the equation has, with initial condition u0, a unique solution which is in this place. So with m plus 2, this script. So it is in m plus 2, so this maybe explains that there is a shift here in the formulation of the theorem. And moreover, it is continuous, and m plus it is continuous as a W2m plus 1 valued function of t, and this estimate is known. So this is a well-known result, and one can refer, for example, to the LP theory result of Nick, but with p equals 2, so in fact not LP but L2, but a consequence of that result. Right, so this is just to formulate the solution, and then the corollary that a classical solution exists if m is greater than 1 plus the dimension half. That follows from Sobolev embedding theorem. Classical solution means that the equation is satisfied in the classical sense, so for almost surely for all t and for all x. And of course some growth condition should be given, for example polynomial growth or condition on the solution. Well, so then there exists a classical solution. Now we would like to solve this equation numerically by using finite difference schemes. So then maybe this notation is also useful to remember. So the finite difference operator is denoted by delta h lambda. Lambda is a vector from Rd, and it acts on a function at a point x. Then one gets 5x plus h times lambda minus phi of x divided by h. So this is defined for any h non-zero and lambda from Rd. So h can be also negative in this definition, and also when lambda equals 0, then it denotes the unit operator. And then together with this equation, we consider the finite difference equation. So du h LH UH T plus F, T depending also of course on X, but I don't try the X, M H, and I don't know, R is an index or super. R, it depends on T, T, U, H, T plus G, T, D, W, R, T with the same initial condition. I think the U has always, so when I write here the T, that is just the same as writing here, so I probably will many times use or abuse the notation. And here, just like before, then the LH T is of this form now, an A printed, let's say, or Gothic A alpha beta, and D, oh, not alpha beta this time, but we index it by lambda and mu, and D H lambda or delta minus H nu, and the summation, as always, with respect to summation convention is used with respect to the repeated indices. I haven't told that, and we take lambda and nu from a fixed set of vectors which contains the 0 as well, and then this summation is over the lambda and mu from this lambda. capital lambda. So this is the difference equation which is considered, and on a grid, the grid is denoted by G sub H, and then so we consider the grid which is generated by these vectors. So H times lambda 1 plus and so on H times lambda k, and then the H is a fixed parameter, and lambda 1, lambda k are from lambda union minus lambda, and k is from 1, 2, and so on. So this is the grid which corresponds to which is considered together with this finite difference scheme. Then the corresponding assumption. So just to remember, this is the 2.3 assumption, and the first one is just again a symmetry, which is a non-important assumption, and then real valued measurability. The second is that we have a similar regularity condition, so 2.3. The first is non-interesting. Second is the regularity, that for fixed m, we have that the derivatives up to order m are bounded, exist and are bounded functions. For L less than or equal to m. And the third one is the stochastic parabolicity condition for the finite difference scheme, where kappa is fixed, non-negative. So here the non-degenerate case is considered today. So this is the G of H, which I have already introduced. And the first remark is about the solvability of this finite difference scheme when it is considered on GH. Then we have an infinite system of stochastic differential equations, and so classical theory gives the solvability, existence and uniqueness, if the initial condition is in L2, and also in L2, little L2, we have the integrability of the, so this condition for the free data. So then there exists a unique solution of this system of equations. The next assumption is the consistency assumption. So here I used A, which in fact I wanted to write with a different way, because these are different functions, not the ones, or in fact I used here A all the time. So what is this B? This is A, and why have I used here the B? In fact, I am afraid that I have a non-correct notation. Oh, no. Sorry. I'm getting, no, the B is all right. The B is here because that is, but it is a different B, not the one which is here in the operator M, because we would like to have the flexibility to approximate the second order and first order operators in many ways. So because we want to have this flexibility, we have to have some consistency between the two operators, so the difference operators and the differential operators, And these consistency conditions are kind of obvious conditions, because what we want is that the difference operators, when h converges to 0, converge to the operators of the SPDE. So therefore, these are obvious conditions. Now, two basic examples here, but there are many other examples. So when we choose the Gothic A when we choose lambda to be the the coordinate vectors plus the 0 vector, and then the usual approximation of the operator, that is the derivative in the direction of the EI coordinate vector is just the difference operator in that direction. So the first example is therefore completely standard. The second is also standard, and but here the new thing is that the first order operators, the coefficients here of the first order operators are with the 0 index. One of the indices is 0, and there we use then two directions. So therefore the approximation which this gives is the symmetric difference for the first order derivation in the direction of the coordinate. And the second order derivations is also made symmetric. So so we have the direction of E sub I, but also the minus E sub I, and accordingly we have then the 1/2 of the derivations in these alpha beta, which corresponds now the EI, EJ directions. 1/2 is in the E sub I, E sub j, and the other half is used in the minus E sub I, E sub j direction. So this is symmetric. An easy statement that this example satisfies the condition. The important thing is to check whether the stochastic parabolicity condition is satisfied, and this is satisfied because the original equation has the stochastic parabolicity condition. So I don't want to spend time on the proof of that exercise. Now the first theorem, which is a slight improvement of a theorem by Yo in 1998, that if the assumptions, these previous assumptions are satisfied with m large enough, larger than 1 plus half of the dimension, then the stochastic difference equation has a unique solution, and moreover, in that sense, approximates the solution of the SPDE. So that means a first order accuracy approximation, what we got in the sense of the supremum norm averaged by the expectation. Now I would like to talk about how to accelerate this conversion, this accuracy, how to get higher accuracy. And here I wanted to show the photo of Louis Fry Richardson, whom I admire, who was a great scientist and also a great person, a great man, who about 100 years ago had the idea how to accelerate numerical methods. Roughly speaking, the idea is that once we have a numerical method which depends on a parameter, like in this case on h, then playing with different values of the parameters like h, h half, h quarter, and so on, and using our method with these values of the parameter, then an appropriate mixture of the approximations will have a much better accuracy. And he even used his method. So he was interested in many subjects, among them in forecasting the weather. So if I remember well, on the 27th of May, 100 years ago, so in 1910, he wanted to wanted to predict from the data obtained early in the morning. In 6 hours, he wanted to predict the weather, so more precisely the pressure. And so he calculated by hand, solving the equations, and that was fantastic. He used his method, but all the calculation was by hand, so without computers. The result was not what happened finally, which is sometimes the case. So he had with about 100 millibar more the pressure, which is enormous, and in fact the pressure remained nearly the same as it was at about in the morning. But then it turned out that if he would have smoothed the data to smooth out the irregularities, then he would have predicted pretty well. So anyway, he did fantastic job, and so I would like to use, or we would like to use his method to the stochastic PD. By the way, just because we are in Cambridge, I would like to mention also that he was a graduate of King's College here in Cambridge. And because we were in York some time ago, he had his secondary school studies in York in a boarding school. All right. So Richardson idea I mentioned, and in fact he used his idea for to accelerate the convergence of finite difference approximations. So this is what we want to do as well, and as far as we know, this is the first result for to implement his method and to justify his method in the case of stochastic partial differential equations. His method is used in numerical analysis for many equations, and not only for finite difference schemes, but many other. So in case of integration, it is called the Romberg method as well, but in fact he did it in 1950, and originally he introduced, Richardson introduced his method in 1910. Well, okay, so what is behind the method? That if there exists a kind of Taylor expansion of the approximation in terms of the parameter, in our case h, then by choosing appropriately the coefficients in the mixture, one can get rid of the lower order terms in h, and this is why one can get the approximation, one can get a higher order approximation. So what we want to do is to find then stochastic field UTH or UTJ, j from 1 to from 0 to k, such that for 0 we have the solution of the SPDE. K is a fixed number, k is a fixed integer, and we would like to have k plus 1 accuracy. So the error we want to have in hk plus 1. So therefore we would like to have such kind of expansion with functions here once again, which UTJ, which are not dependent on h. The remainder term can depend on h, and it depends, obviously, or normally it depends on h, but it should be estimated independently on H. So this is what we want to achieve, and then the result is the following, that if the above assumptions, so what I try to write down and remind you, if these assumptions are satisfied with M, which measures the regularity of the free data and the coefficients and the initial condition, if M is large enough, that is larger than that K, the parameter of the accuracy, and so the level of the accuracy larger than K plus 1 plus the dimension half, then such an expansion exists, and moreover the remainder term can be estimated by that Km, which somewhere there you can see Km star, and the constant n is independent on H. It depends only on the set lambda, d, and k, and t. And of course, if we have this, then a very simple linear algebra solving a linear system of linear equations gives us that if we take that mixture, which is denoted by U bar H, where the coefficients can be determined once forever, that is here the definition is just take the Wandermann matrix V, defined like this, apply it to the unit vector or basis vector 1, 0, 0, 0, and then we obtain these coefficients, and then with these coefficients, using the solutions, the approximations corresponding to H half, H quarter, and so on. So this means that the approximation corresponds to these ones. Then the accuracy is K plus 1. So the order of accuracy is K plus 1. Well, maybe one more thing, that in the equation, in the second example, we can see that many terms in the Taylor expansion are missing. More precisely, the terms which correspond to the odd powers are missing. It is easy to see that this fact, if we notice that the difference equation, if we change h to minus h in the second example, remains the same. From here one can get that then the expansion must remain the same, and from here one gets that then every odd power coefficient disappear. So in this case, of course, one can have fewer number, roughly half of that, to mix in order to get the same accuracy, so level or order of accuracy k. Right, so this is the theorem which corresponds to that one. So if we use again the mixture I have written in the previous one, sorry, this one, so this is the tilde, and now the difference is we have fewer terms, and here it is defined by 4 here instead of 2. Then we have the same accuracy for this mixture, and just an example that in the case of example 2, if we take just 2 terms in this mixture, we get already h to the 4 accuracy. Well, an example to see that this method, at least in case of this toy example, works, that let us consider this simple stochastic differential equation in one dimension. So d is the derivation in x, so that is just 3 times the one-dimensional Laplacian and twice the derivation in x. Initial condition is cosine x, and this is the difference equation, stochastic difference equation. And then it turns out that if we take t equals 1 and h is just 0.1, and suppose for simplicity that the w at 1 at some omega is 0, then the solution is equals to this here, of course approximately, but up to these many, I don't know, 10 or how many, 10 digits. And the approximation when we have h is this one. When we have h half is this one. You can see the 7, up to 7 is all right, but then it's already not. But when we do the mixing, then we have up to this 7 here, correct? So and it is interesting to mention that this level of accuracy is achieved for an h with this h, or instead of this h with a much smaller one, so 15 times smaller than the h half, so the 0.05. So it increases the accuracy, at least in this toy example, dramatically. Also, just mentioning that obviously if we have the expansion and we apply to it a difference operator of any order, so this means lambda 1, lambda n are vectors, so lambda to the n is the set now, and so we n order difference we take of the approximation, then obviously we have the expansion for it as well. The only question whether this can be estimated independently of h in order to get expansion and acceleration also for the differences of the approximations. And the following theorem says that yes, if we require more derivative, so that is n with n more derivative, then we have the estimate for the remainder term, and also then we get that not only the solution but its differences can be approximated with accuracy k plus 1. Yes, maybe just one, if I remember well, we were 45, that was what I read in the last email. So about the proof, only one thing, that one of the main ingredients is that we should study the solutions and the regularity property of the stochastic difference equation. The idea is that it is good to consider it not only on the grid but on the whole space, so to understand it for each x, and then to prove existence and uniqueness and regularity result for it, because that is, as it is usual in numerical methods for linear equations, one should consider the residuum, what the residuum gives when one puts it into the difference equation, which is when one uses the scheme itself. And so therefore here as well we consider the stochastic difference equation, and then we prove that there exists a unique solution which is a Wm2 valued continuous process, and we have an estimate which is here n independent of h. And so this is one of the basic ingredient. And anyway, my time is just about over, so I finish here. Thank you very much.
There are some questions?
So, if your m is small, can
M.
regularity,
Mama.
can you speed up your conversion somehow, maybe differently, or?
If if m is not large enough,
Yes.
that is the question. At least a general result for that we don't know. Here it is very important that m should be so the coefficients and the free data should be regular enough, so smooth enough, because we have everything is based on the Taylor expansion. So therefore, so the higher accuracy we want, the higher smoothness we have to require in a general scheme. In some special one, whether there is some miracle, that I don't know.
I have a simple question. Are approximations non-negative?
Sorry.
Are your approximations u sub h non-negative?
Oh yes, that's that question. You mean when we apply this to the filtering equation in that case, or so when we have so initial value is non-negative. Yes, that is your no. In general, here not. But in the case which we did for deterministic PDEs, when we have monotone schemes, then that is the case. But here in general, I don't think it is the case.
Does it matter?
Sorry?
Does it matter at all that they
In
are
case
not-
of
You asked.
That's a question. Should we keep them non-negative? It's irrelevant.
Don't know. I haven't thought about that. Don't know. Maybe in filtering it can play a role.
It depends on the application. If gamma is
Yeah.
a probability or a normalized probability. Important for depending the physical interpretation of the PDE.
So it can play a role from point of view of applications.
Did you say you are also truncating the grid? I mean, you only take a finite. You do work with the infinite grid or the finite grid?
No, here, this is a kind of theoretical result, yes, because here we do, the next step is to truncate, and so the truncation gives an error, so one should go quite far if one would like to keep the accuracy low, high, sorry, the accuracy. So that's another component.
You're
But
going through the acceleration with the Richardson method. Do you expect that the truncation will have to be larger and larger, or is it going to be?
no, if we would like to approximate the original equation, so if we would like to approximate the original one, then the truncation should be larger and larger if one would like to have a good accuracy for the original one.
But actually not enormously large, not enormously large. The decay is exponential and not even exponential, as e to the minus x squared. The decay, if you are interested in this value of solution at the origin, then what is going on as far is contributing very significantly.
Well,
Very little.
you cannot risk it because in the filtering case you have to follow the signal, and that signal has a very strong drift. Then you have to have a huge drift to make sure that you follow the signal. It's not because of the diffusion part, but because you have to follow the signal.
Yes, but for the Zaka, you decrease it. If you normalize it,
Yeah, there is also that we should normalize, so that means that should be approximated as well, so the integral should be approximated as well. So there again, a Richardson approximation can be used, or Romberg approximation, to get that part as well, but I'm not talking about that.